Hey physicists, so we've been looking at some uniform circular motion problems, but haven't really put in any numbers. And so that's what we're going to do right now. So we've talked about the force that's keeping an object in circular motion. And you may have been asking yourself, what might affect the magnitude of that force keeping an object in uniform circular motion? So if you brainstorm a little bit, you might come up with some ideas. There are three things that often, when we have this conversation in class, come up. The first one is mass. So if you think about it, if I take a little cup of water and I spin it versus taking a big bucket of water and spin it, which one is going to require more tension on that rope? We think about that probably as we increase the mass of the object that's spinning in a circle, it makes sense to you, hopefully, that the force is also going to increase. Another thing that also might increase the force, or change the force, I should say, required when using uniform circular motion is the radius. And the classic example that I think about with this is if you have your keys or something else on a lanyard and you start spinning it in your fingers, that's kind of something we always do. As you spin it and it gets smaller and smaller, like you spin it around your finger, as the radius goes up, sometimes it makes it easier, I should say, if the radius is going up to spin it. The force actually goes down. The one that I'm actually thinking about, the reason I paused was because usually you make the radius smaller and smaller, and then you can kind of feel the tension in that lanyard getting higher and higher. So we know that those two are inverses, whereas in the first case, it is a direct relationship. And there's one other thing that may affect the force that's required to keep something in circular motion, and that's how fast it's going, the velocity of the object that's going in circular motion. The faster you go, if you're spinning something around and around really, really fast, may make sense that the tension in that string is going to get really, really high, right? If you spin it too fast and you have a string that is about to break, then it actually could break because we could exceed the tension that string can exert. So as you increase the velocity, hopefully it makes sense that also the force would increase. So those are the three big things that are that need to be taken into account when we talk about the force of something in uniform circular motion. So we can write this out here. So the force required to keep an object in uniform circular motion, this would be a great thing for you to write down if you're not doing so already, okay? It has to do with the mass, the radius, and the velocity. And if we put those things together, we can say that the force is equal to, so the mass is going to go up as the force or the force is going to go up as the mass goes up. We just said that. Also, the velocity is going to cause the force to increase. It happens to be as a squared. If you want to know the details of that, let me know or let your teacher know, and we'd be very happy to show you how. But for now, we're just going to leave it right there. And then the last thing is the radius. And remember, we said that the radius and the force are inversely related, so that's why it's going to go in the denominator. Okay, so this is just kind of a nice thing to know, a nice thing to utilize. And then we're going to be a little clever here and say, oh yeah, and we also know that Newton's first and second law, you remember that from a few months ago, we said that the net force acting on an object was equal to the mass times the acceleration. We know that the acceleration, when we're talking about uniform circular motion, is that centripetal acceleration. Remember, we talked about that not too long ago. And so if we take a look at this nice lineup here, you can see that this lines up super nicely with the acceleration, the centripetal acceleration. And so from this, we can kind of reason here that the centripetal acceleration, so that would be the acceleration of an object moving in uniform circular motion, is equal to the velocity squared of the object as it's rotating, divided by the radius of the circle that it's going in. So I'm going to put a big box around that. I'm going to also just label this as the formula for centripetal acceleration. So hopefully that makes some decent sense. There are a couple of problems in your textbook, some example problems that I would encourage you to take a look at. They are on page 288, numbers 1 and 2, and page 230. numbers 1 and 2 as well. And there are answers to these questions. I'm just going to write this down. Answers on Canvas, answers and solutions. So something to look for there. And then actually questions 3 and 4 in both of those sets were part of your homework as well. So that'll give you something to work on, just some fairly simple problems to take a look at so that you can feel good about doing those calculations. Once you've done that, once you feel good about it, then take a look at the next video so we can look at a couple of examples. Thanks.